Hello, my name is Vincent Rolliard. I'm making a small video to give you a preview of the content of the course on packaging and distribution dynamics that I'll be presenting at Virginia Tech University in the US in June this year. These are the learning outcomes for this course, which is focused on giving you a set of tools as well as a confidence to properly select instrumentation and use the instrumentation to measure a variety of distribution hazards, to confidently apply correct engineering principles and protocols so that the measurements you make on these complex dynamic processes give you the right information to be able to characterize the distribution hazards. You will also be able to undertake mature and sophisticated analysis of measured distribution hazards as well as interpret them in a packaging context. We'll be dealing with laboratory vibration and shock testing, and at the end of the course you should be able to critically assess various test protocols and make sure that you apply the correct test in a correct way that suits your product and your scenario. We'll start off the course by looking at some engineering fundamentals, looking at how products and packaging systems can be modeled as mechanical systems. For instance, this animation uses these modeling techniques to predict not only the motion of a stack of boxes on a vibrating platform, but also enables us to calculate the contact forces between the boxes. Using these mathematical models can be very useful. For example, modeling packaging systems allow us to predict their response due to an impact for various material properties. Next, we'll be learning about harmonic motion, the Fourier transform in the context of vibration, and we'll be using a number of hands-on practical demonstration to help you understand difficult concepts. In this case, I'm using a real-time frequency analyzer which I've designed myself to help you understand this by using an audio signal as an input. For instance, I'm playing brown noise which is being picked up by the microphone as well as my voice, and you can see on this bottom graph the equivalent frequency spectrum. If I introduce a sine wave into the sound, you will see a peak near 500 Hertz, which is being picked up by the spectrum analyzer. And this is exactly the same principle we use, or same technique we use to analyze track vibration or vibration of any vehicle. We'll be spending quite some time learning about instrumentation and digitization, with the aim of making sure that at the end of the course you'll be able to not only select the correct instrument to do a measurement, but also to be able to set up the instrument properly. We'll be looking at important and practical issues when it comes to measuring dynamic events, shock and vibrations. We'll be looking at sensor range, sensor resolution, sensor dynamic range, sensor frequency response, among many other parameters. We'll be spending some time learning how frequency filters work and how to use them properly. Especially, we'll be looking at how setting frequency filters in different ways can affect your signal, again making sure that pitfalls are avoided. We'll be looking at how to analyze random signal in a practical sense, focusing on frequency domain analysis, such as how the power density spectrum is calculated. For that, we'll be using real signal and calculating the average power spectral density function using various parameters. And what we'll also do is learn how to interpret these PSD functions, looking at the peaks, what type of peaks they are, where the peaks are, what frequencies. Vehicle shock and vibration can be quite complex, and we'll be looking at ways to identify and deal with occasional unpredictable shocks that can sometimes occur. Given the complexity of vibrations generated by transport vehicles, we'll be looking at various statistical analysis approaches. Here, this graph shows you for a real measured data set the real values of a moving RMS, a moving crest factor, moving kurtosis parameter, and these will help us better understand how the vibration intensity varies during a trip. We'll be spending quite some time using specialist software to analyze real measured vibration data. And this is one example with a vibration record where we will analyze the moving RMS. We'll be looking at the power spectral density function. We'll be looking at the statistical distributions of the RMS, and also we'll be looking at the properties of the signal itself in a statistical domain. Finally, we'll be looking at the variety of ways that distribution hazards can be simulated or reproduced in the laboratory for product testing. I'll spend some time explaining to you how vibration controllers and vibration test systems work, how to interpret the various test PSD functions that are proposed in various test standards. We'll be looking at more recent developments related to the shape of the power spectral density function for vibration testing. We'll be looking at RMS levels and test duration, and also we'll be looking at a more sophisticated way of setting the test duration and RMS level for testing in order to enable you to do more optimized testing for products and packages. I hope this was a useful preview of the course, and I look forward to seeing you in Virginia in June.